Hi everyone, my name is Xiangrui. I'm a graduate student from Huazhong University of Science and Technology. And today I will talk about our work rethinking the request to I/O transformation process of high system for full utilization of high bandwidth SSDs. Well, over the past few years, we have witnessed the explosion in SSD bandwidth. We have moved from the days of SATA SSD with less than 1 gigabytes per second to today with PCIe 5.0 SSD with over 10 gigabytes per second. What's more, the cost per byte has remained relatively stable. This makes high bandwidth SSD a cost-efficient solution widely deployed in many industries like IoT devices, mobile devices, and larger data centers. This begs the question, how can today's diverse application truly leverage these high bandwidth SSDs? Well, as we all know, today's data-intensive application like graph processing, scientific computing, and cloud computing often generate requests with various sizes and offsets. Despite the tenfold increase in SSD bandwidth, our storage systems are still using legacy I/O stacks. So we have to ask, is this improved SSD performance really directly translating to better application performance? Let's take a look. We ran a single threaded test focusing on random writes between 1 byte and 2 megabytes. And here's what we found. The throughput of the 4 file system we tested only reached a third or quarter of the underlying SSD. Naturally, we thought, maybe the small writes are to blame, right? Maybe the small writes are the bottleneck. So we tweaked our test, focusing on writes between 0.9 megabytes to 1.1 megabytes. Even then, the improvement was minimal. And we were still far from the SSD's raw bandwidth. Clearly, there's more going on here. The file system used page cache to transform user requests into memory page aligned BIOS. But consider a non-page aligned write. The online portion requires a slow read-modify-write operation. That means reading from the SSD, modifying in memory page, and then writing back. Because of the long latency of SSD access, these small reads are incredibly slow, and this becomes a major bottleneck. Now remember, our previous test has sufficient memory and no sync cost. This means that writes were being asynchronously flushed, and our performance result were primarily from the page cache. So no matter how high the bandwidth of the underlying SSD is, the performance is limited in this scenario. This led us to investigate actual write performance hidden by the page cache. We added fsync for each write. The results are striking. The write latency was almost 9 times higher than the raw SSD I/O latency. This confirms our hypothesis. File systems are failing to deliver the full potential of high bandwidth SSDs. And we call this phenomenon write inefficiency. And this is not only for our unaligned writes. This is also true for aligned large writes. So we really want to know what is the root cause of this write inefficiency. First, we use direct I/O mode to exclude the impact of page cache and compare the aligned and unaligned direct I/O writes. For the unaligned writes, we use a read-modify-write operation similar to what page cache does. To align the writes on the host side. The result shows that the latency of unaligned writes is almost 9 times higher than the aligned ones. This is because each unaligned write requires 1 or 2 small SSD reads. And as the write size increases, the SSD read latency becomes less significant. However, even with 1 megabyte large writes, small SSD reads can still cause an 80% increase in the write latency. To analyze the page cache overhead, we performed a breakdown analysis for ext4 and f2fs. As expected, the alignment overhead matches what we discussed earlier, and this is shown by the tail bar on the top. We also found that as the write size increases, the page cache overhead becomes more significant. For example, for the 1 megabyte writes, the page cache overhead accounts for almost 40% of the overall overall write time, which is equal to the time spent on SSD IOs. Additionally, the fsync cost overhead is also significant. In the 1 megabytes write case, over 60% of the time is spent on page cache management and BIOS assembly of fsyncs. And we think these are the key factors contributing to writing efficiency. For comparison, we use the direct I/O mode for aligned writes to observe the time composition. And the result shows that most of the time is spent on block IOs. Moreover, the fsync core overhead is minimal in this case because there was no need to look up the dirty pages. However, despite avoiding page cache overhead, direct IO's strict alignment requirements are hard to meet. So we will discuss this later. Next, we examine a commonly overlooked factor, SSD I/O concurrency. Most storage systems passively utilize the internal parallelism of SSD. However, due to the internal complexity of I/O scheduling, a single I/O thread can hardly maximize the SSD performance. To verify this, we test two I/O patterns. First, a single thread with large aligned IOs. Second, multiple threads handling smaller 32 kilobytes I/O for each large request. The result shows that whether for reading or writing, the multi-threaded I/O pattern was able to better utilize the SSD performance. The higher the SSD bandwidth is, the more noticeable this effect became. However, most existing storage system does not consider actively providing sufficient I/O concurrency. Naturally, we are motivated to design a solution that maximizes the performance of high bandwidth SSD. And from our early analysis, we identified three key issues to address. First, high I/O alignment overhead, and second, high page cache overhead, and last, insufficient I/O concurrency. For the first issue, an intuitive idea is to merge writes in memory and asynchronously write them back. However, this sacrifices the persistence and wastes the high bandwidth provided by SSD. What we really want is to maximize the use of the underlying SSDs. For the second issue, a straightforward approach is to use direct I/O mode to bypass the page cache. However, this is not clear how to efficiently meet its strict alignment requirements of direct I/O. For the third issue, an obvious solution is to actively I/O splitting and multi-threaded I/O processing. But again, the implementation isn't trivial. The I/O alignment issue is widespread and cannot be avoided as it's application-driven. We can't change the user behavior, and we cannot change the fact that the SSD required alignment access. So we need to bring in some help. Specifically, our solution is to introduce NVM as auxiliary storage to assist with I/O alignment. Specifically, we transform any file writes into aligned SSD IOs and unaligned NVM IOs. Furthermore, we will use direct I/O mode and multi-threaded I/O processing to handle SSD IOs. These transformed SSD IOs are always aligned, making it easy to enable direct I/O mode. Our key idea is to partition writes instead of merging them, and directly leverage the underlying SSD high bandwidth. Therefore, we propose ORCFS, an SSD NVM heterogeneous orchestrated file system. The key techniques includes heterogeneous data layout, file write partition, unified per file mapping structure, and a parallel I/O engine. First, let's look at a heterogeneous data layout. In our file system, all metadata is located on the NVM side, while the data is placed across both NVM and SSD. We introduce three types of storage units: NVM pages, NVMe pages, and SSD blocks. The SSD blocks are used for 32 kilobytes aligned data segments. NVM pages are used for 4 kilobytes aligned data segments. And NVMe pages are used for the remaining unaligned data segments. Next, we design a file write partition strategy. It partition writes into block-aligned SSD IOs, page-aligned NVM IOs, and the unaligned chunk IOs. It then sends these IOs to their respective storage units, that is to say SSD blocks, NVM pages, and NVMe pages. Due to the complex user write patterns and a combination of various write requests, we proposed two policy to guide our split partition strategy. First is alignment prioritizing policy, and the second is fragmentation minimizing policy. The alignment prioritizing policy means partition requests in the order of priority from blocks to pages and U pages. The fragmentation minimizing policy means placing files in as few storage units as possible. You can refer to our paper for details. Because we are using 3 types of storage units, this complicates file mapping. So we introduce a unified per file mapping structure called HR tree. HR tree is used to map a file logical offset to block pages and U pages simultaneously. It consists of a legacy radix tree and a heterogeneous layer at the bottom. The radix tree part maps a file logical offset to a logical block. The heterogeneous layer records the data composition of a logical block. With HR tree, ORCFS only need to perform a single tree traversal to locate all storage units associated with a file request. To efficiently and transparently handle the partitioned heterogeneous IOs while ensuring data consistency, we develop a parallel IO engine. First, the parallel IO engine processes SSD IOs and NVM IOs in parallel. Secondly, it actively uses multi-threaded IO processing to handle SSD IOs. To ensure data consistency, each IO thread uniquely executes IO within its exclusive data range. Furthermore, ORCFS develops triple data fast for IO execution, using direct IO mode for SSD writes, and using buffered IO mode for SSD reads, using popular memory semantic paths for NVM access. We will show the benefit of the SSD read path choice later in our evaluation part. In addition, we have incorporated several other designs and optimizations, including file data defragmentation, index optimization, file system architecture optimization, and more. Please refer to our paper for details. Now let's look at the experimental results. We set up 3 categories of file system as baseline for comprehensive comparison. For the SSD file system, we choose ext4 and f2fs. For NVM file system, we choose Nova, ODINFS, and ArcFS. For hybrid file system, we choose Strata, SPFS, and PHFX. Note that we implement PHFS based on ORCFS. It places all metadata on the NVMs and use NVM to handle small writes and SSD to handle large writes. PHFS used to demonstrate the design advantage of ORCFS. First, let's examine the single-threaded random write performance. This graph shows the average write latency. Compared to the 3 categories of file system, ORCFS consistently shows significant advantages. And let's further verify the source of ORCFS performance. As the table shows, the larger the write request, the more data is written directly to SSD. For example, in 1 megabyte case, over 90% of the data is written directly to SSD. And this means that in large write case, most of ORCFS performance stems from the underlying SSD. This is different from the sort of file system like Strata and SPFS, where most of the performance comes from the expensive NVMs. Now let's look at ORCFS read performance. The test file writes with corresponding write size and then perform random reads. You can see in figure A and B, the peak read throughput of ORCFS is significantly higher than the baseline file system. This indicates that ORCFS SSD read passively benefit from aligned pre-filled writes. Because the data placement in SSD side is always 32 kilobytes aligned, it allows page cache to work much more efficiently. And this explains why we choose buffered I/O mode for SSD reads. Let's move on to multi-threaded random write performance. The result shows that in large write case, ORCFS needs a small number of user threads to maximize SSD performance. This demonstrates that ORCFS utilizes the full performance SSD by actively increasing I/O concurrency. Finally, let's see how ORCFS performs with real-world applications. level DB workloads is full of small requests. OrcFS uses NVM to handle the majority of the requests, while the large compaction writes are handled quickly by the SSD. As a result, OrcFS performs exceptionally well across all workloads. For graph processing workload, it has a mixture of large and small requests. Our file system significantly reduced the processing time by up to almost 70%. In summary, we reported and identified the writing efficiency of file system on high bandwidth SSD, and we explored its root causes. We presented OrcFS, a novel file system designed to overcome its writing efficiency and maximize SSD performance. OrcFS achieved a significant improvement on both write and read performance. And furthermore, our work has been open sourced, and you can check it out on this link. And thank you for your time and attention. I'm opening questions.